Okay, so let's dive in. Adapting these enormous pre-trained AI models, it's a huge challenge, computationally speaking. It can just gobble up resources.
Absolutely. And that's really where these parameter efficient fine-tuning methods, PFT methods, have become so important.
Right, and LoRa, low-rank adaptation, that's been a really popular one. Simple, often works well.
It's been widely adopted.
Hmm.
But it does have this known issue, instability during training. It's kind of its Achilles heel.
Instability. And that often comes down to these scale disparities, right,
Mm.
between the two matrices LoRa uses.
Exactly. The A and B matrices. Research shows they often end up operating at very different scales, which can mess with the optimization.
Leading to things like vanishing gradients or exploding ones.
Precisely. Or just performance that isn't quite optimal. It makes the whole process less reliable than you'd want.
Which brings us to SingLoRa. This is pitched as a solution to exactly these stability problems.
It is. It's a really interesting new approach. The claim is it inherently ensures stable optimization, and maybe just as importantly, it cuts down the number of parameters you need to train.
Okay, so stable and more efficient. That sounds promising. For this deep dive, then, let's really unpack how SingLoRa actually achieves this and, what does the performance look like in practice?
Sounds good. To really get SingLoRA, maybe we should quickly recap how standard LoRa works first.
Good idea. Remind us of the basic mechanism.
Sure. So LoRa doesn't change the original huge weight matrices in the model. It keeps them frozen. Instead, it adds a small update, which is the product of two much smaller matrices. Let's call them B and A.
E times A.
Right. B might be, say, DXR, and A is RXK, where
Yeah.
R, the rank, is much, much smaller than the original dimensions D or K.
So you only train these small A and B matrices. That's the efficiency part.
That's the core idea for efficiency. But, as we said, it's this B times A structure, these two separate matrices, that leads to the instability.
The scale disparities again.
Uh-huh. They just learn at different rates, different magnitudes. It makes life difficult for the optimizer. People have tried fixes, of course.
Like LoRa plus score using different learning rates.
Yeah, different learning rates for A and B, or trying specialized optimizers. And there was other work, like Laura Donerite, pointing out that even for the same final update matrix, there could be multiple different ways the optimizer sees the gradients for A and B, adding to the instability.
Okay, so it's a known, tricky problem. How does SingLoRA rethink this fundamentally? What's the core change?
It's actually quite elegant in its simplicity. Instead of B times A, SingLoRA uses just one low-rank matrix, let's call it A again, and it forms a symmetric update, A times A transpose, so AAA.
Yeah, just one matrix, A, used twice in a symmetric way.
Exactly. By having only one matrix to learn, you inherently eliminate that problem of conflicting scales between two different matrices.
Yeah.
It's stable by construction, really.
That makes intuitive sense. So the immediate advantages are clear then. First, you get rid of that core instability driver.
Right. Stable optimization becomes much more straightforward,
And second, you're only learning one matrix instead of two.
which roughly halves the number of parameters you need to train compared to standard LoRa. A big win for efficiency, especially with massive models.
Okay, having parameters is definitely significant. But let's talk more about the stability. You said it's sort of guaranteed stable feature learning. How does that work theoretically?
So, yeah, within the theory of very wide neural networks, infinite width networks, SingLoRa's design provides this guarantee. It basically means that as you train, the changes in the model's output stay bounded. They don't vanish, they don't explode.
It keeps the learning process predictable.
Exactly. Controlled and predictable. And a practical upshot of this is that you don't usually need all the complex tuning that LoRa sometimes requires.
Like fiddling endlessly with learning rates or needing special optimizers?
Right. SingLoRa seems to work well with standard optimizers like SGD or AtomW, often without needing lots of hyperparameter tweaking. It simplifies things.
You also mentioned transformation invariance. How does that tie into stability?
Ah, right. So with LoRa, the B times A structure means you could have different pairs of B and A matrices that mathematically result in the same overall update.
Okay.
But crucially, the optimizer might see different gradient paths for these different pairs, which can cause instability. SingLoRa's AA formulation avoids this. It's transformation invariant for gradient descent, meaning the optimizer behaves consistently, resolving that source of instability.
And it's flexible, too. It works beyond just square matrices.
Yes, the approach can be extended to non-square matrices, so it's applicable to various architectures, not just specific layers.
The theory sounds really solid, but, the proof is in the pudding. How does SingLoRa actually perform when tested on real tasks? Let's start with language models.
Yeah, the results are quite strong. Take Llama 7B, a pretty standard large language model, fine-tuning it on the MNLI common sense reasoning task.
Okay.
SingLoRA hit 91.3% accuracy. Compare that to standard LoRa at 89.1% and LoRa Plus at 90.2%.
So a noticeable improvement in accuracy.
Yes, and importantly, it did this using only about 60% of the trainable parameters that LoRa and LoRa Plus used. Better accuracy with fewer parameters, that's a big deal for LLMs.
Definitely. What about on smaller models, maybe on benchmarks like GLUE?
Similar story there. On models like Roberta Base and GPT-2, tested across the GLU benchmark suite, SingLoRA showed consistent gains. About 0.9% average accuracy improvement for Roberta and 1.1% for GPT-2 compared to LoRa, LoRa plus Bera, and even another method called DoRA.
And again, using fewer parameters.
Again, using roughly half the trainable parameters of the others.
Wow. And did it need lots of tuning to get those results?
That's another key finding. The researchers reported using a single learning rate for SingLoRA across all these different models and datasets.
Really? Unlike LoRa and LoRa Plus, where you often need extensive searches for the right learning rates for each specific setup.
Exactly. LoRa and LoRa Plus needed careful per-task tuning. SingLoRA's ability to perform well with a single setting really underscores its robustness and the stability of its optimization.
That simplifies the practical application immensely. Less hyperparameter searching is always welcome. Okay, so strong results in language. Does this translate to other domains like image generation?
It seems to. They tested it with Stable Diffusion v1.5, fine-tuning on the DreamBooth dataset for personalized image generation.
How'd it fare there?
They looked at DINO similarity scores, which measure how well the generated image matches the target concept. SingLoRA scored 0.151.
How does that compare?
It was better than DoRA at 0.148 and standard LoRa at 0.143, so again, indicating better performance in capturing the desired object features.
Any visual examples that stand out?
They mentioned a specific case trying to generate a shoe with an iridescent color. Apparently, SingLoRA did a better job preserving that fine, specific detail compared to the other methods.
Interesting. So it seems versatile. Now, going back to stability you mentioned earlier, the theoretical promise, did they show empirical evidence of this stability across different learning rates?
They did. There was an experiment fine-tuning Llama 7B on MNLI again, but this time sweeping across a wide range of learning rates.
And what happened?
SingLoRA's final accuracy was remarkably consistent. It only fluctuated by about 1% across that whole range of learning rates.
Only 1% variation. How did LoRa do in the same test?
LoRa's accuracy swung much more wildly, varying by up to 4.8%.
Okay, that's a pretty clear demonstration. SingLoRA is just much less sensitive to the learning rate choice.
It really highlights the more robust optimization dynamics that the single matrix design enables.
One potential question, though. SingLoRA uses this symmetric update, AAA. Does that symmetry limit what the model can learn, especially in something complex like a transformer's attention mechanism? Does it force attention patterns to be symmetric?
That's a really good question, a natural concern. While the updates to the query and key matrices themselves might be symmetric like AQA and AKA, the way they interact in the attention calculation is actually more general. Because the final attention score depends on the product, essentially Q times K transpose, QKT. And the product of two symmetric matrices isn't necessarily symmetric itself unless they happen to commute, which isn't generally the case here.
Ah, okay. So even with symmetric building blocks, the resulting attention transformation can still be non-symmetric and general.
That's the idea. It doesn't appear to fundamentally restrict the model's ability to learn diverse attention patterns. They even ran a synthetic experiment designed to test if SingLoRA could approximate arbitrary matrices compared to LoRa.
And the result?
SingLoRA actually converged faster and achieved better final approximation accuracy than LoRa in that test.
So the symmetry doesn't seem to be a practical limitation on expressiveness and might even help convergence.
It seems that way based on these findings.
Okay, so let's try and bring this all together. SingLoRA introduces this, well, conceptually simpler approach to low-rank adaptation. Just one matrix, A, forming AA.
Right, and this simple change tackles LoRa's main weakness, the instability from scale disparities, head-on.
Leading to empirically better performance in both language and vision tasks we looked at.
Yes, better accuracy, often achieved with significantly fewer trainable parameters, roughly half in many cases.
And, crucially, a much simpler, more robust optimization process. Less need for that painstaking hyperparameter tuning.
It definitely seems to lower the barrier to getting good results reliably.
So, as we wrap up, here's something interesting to think about. The paper suggests SingLoRa's approach isn't necessarily mutually exclusive with other LoRa improvements. They mention it's potentially complementary to methods like DoRA, for example.
That's a fascinating point.
It does make you wonder, could combining SingLoRa's stable foundation with techniques from other variants lead to even greater gains in efficiency and performance down the line? That seems like a really promising avenue for future exploration.